Hello everyone, this is Jishen Yang. I am recording this video for the course project of Advanced Computer Networks, CSA 220 for the semester of 2024. I'm gonna introduce myself first. I am a PhD student in the Department of Computer Science, Georgia State University, and this is my fourth semester. And my team member contains other three people: Lu Guangxi, Han Jingkun, and Zhou Zhibo. So this presentation will be about the paper Strongly Secure and Efficient Range Queries in Cloud Database Under Multiple Keys. This paper is first published in 2019 on the conference of InfoComm IEEE and is proposed by authors of Chen and others. So this presentation will through the outline of 5 parts. The first is the background information, then it's the introduction with the motivation of this paper and how roughly this paper is designed, and then the system model, how exactly the system is structured, and the theoretical analysis of it, and then it's the experiment results. So how the authors implement the model into the simulation and how the simulation illustrates the results of demonstrating how efficient and effective the proposed model is towarding the realistic scenarios. And then finally the conclusion. So firstly is the background information. We're living an era of big data. The data amount is booming. According to IDC study, the total amount of data in 2018 has a volume of 33 gigabytes, and expectedly the volume will grow up to 175 gigabytes by the age of 2025. So the amount of data is growing exponentially, and with this big amount of data, we can utilize the volume and all the data to to discover more of the value containing it. And the data science has developed thanks to more and more sources to be studied from. Then, so to deal with this variety and volume of data, SQL is a very popular language and framework. It is particularly useful in handling structured data, which is the data incorporating relations among entities and variables. And the cloud-based dataset is now considered as a promising technique to process rich SQL queries on remote data. There's several advantages of the cloud computing. The first one is the cost. The cost will be relatively lower than storing and analyzing, processing the data all locally, because all the servers of the cloud computing will be located at a place which has a lower cost of electricity and space. And then is the speed. Also, the cloud computing, all the servers will be stored in a place that the speed and all the performance will be optimized. Then is the productivity, because on the cloud computing, it always comes with the cloud storage, which enables all the researchers and workers, they can collaborate together without the constraints of the geographical locations and other obstacles. So once they got online, they can all dealing with the same task at the same time. And in this way, the efficiency will be greatly improved. Then the reliability, because if all the data is stored and processed locally, once the server or the storage device is damaged by any of the causes, all the data will be gone. But on the cloud computing and storage, the data will be stored in different locations, and also the risk of the device got damaged is much lower. And also because the commercial use of the cloud, the cloud service providers, Amazon's and Google and Microsoft, they probably and most likely have the insurance coverage which can make up some of the damage or the loss if ever the data is damaged. And finally, and probably the most importantly, is the security, because many cloud providers offer a broad set of policies, technologies, and controls that strengthen your security posture overall, helping protect the data, apps, and infrastructure from potential threats. So, the cloud is getting more and more popular, not only because of the efficiency, also the security guarantees is very, very important nowadays in both of the data science and other like developments based on the data. So here comes the concept, and also which is the most important motivation for this paper, is the data security. So advances in cloud computing have recently enabled users to outsource their data to clouds for large-scale data storage, management, and query processing. With recent incidents of massive data breach, however, privacy concerns hinder the adoption of cloud paradigm. In this paper, the authors introduce a technique to provide solution to data privacy concerns, which is the security cloud database under multiple keys for range queries, and for brevity is MKSDB. And this system is constructed on a two-cloud architecture and a novel distributed two-trapdoor public key crypto system. And notably, the author pointed out that because it's a two-cloud structure, so when implementing it, the two cloud will be from the two different cloud service providers, such as Google and Amazon, who are rivals and who are very unlikely to collaborate with each other and sharing the private informations. This is a good point. And then it's an example of how the system is going to work. The clients can encrypt origin data or query conditions and decrypt the results with their respective keys. Meanwhile, the RAND queries can be evaluated on the multi-key encryption data effectively. So let's consider a real-world example for a health medical database below. So they got 5 data entries: Ada, B, Carl, Deb, and Ida. All the information, the features for each data entry are encrypted by public key 1 to 3. So it's a pool of patient records in a cloud database for clinical research, and also for computing global characteristics. While each hospital prefer not to disclose the private data to other participants, the encrypted relation patients is shown as like the following the chart. So the the PBBQ is a pre-breakfast blood glucose management, and the PLBQ is the pre-lunch blood pressure, and the PS is the pre-supper. So after the encryption, the actual uh, the exact number of the feature, the exact value of the feature will be covered, but it'll be transferred into a encrypted uh, relationship. So the range query can still exist and be conducted. So then is the system model. Figure 1 presents the system architecture of the MKSDB, the proposed model. We assume the existence of two non-collusion, semi-honest cloud providers, which are Amazon and the Google, S1 and S2, where S1 maintains an encrypted database contributed by multiple clients, and S2 provides crypto services. In addition, the green block was not originally contained by the figure 1. This is a trusted key generation center in the system, which is only used to manage public and private keys. And on the right part is a table illustrating how uh, how many good properties the proposed model has. There's the data and query privacy, semantic security, hiding data access pattern, multiple keys, range query, and scalability. And then this is the preliminary. To simplify the description of the protocol, the model only considers a simple case of two clients. One acts as a data contributor, which is the client C, and then a data user, which is a client U. So for figure 2, this graph is very useful and sufficient to demonstrate the general scenario. And the table 2 is the system notations, all the keys, and the decryption and encryption process. And the figure 2 is the initialization of the database. So the key GC is the key generation center. Firstly, the participants can get the deserved public keys and private keys from the key generation center, and then client C, which is the data contributor, encrypts the records locally and uploads them to the database located in Cloud S1. And now the encrypted query can be issued by client U, which is the data user. After this, the Cloud S1 and Cloud S2 cooperate to run secure query protocol and ultimately return the encrypted result to client U. Among all the clients, only client U is able to decrypt the results. And then the model contains 3 steps. So the query consists by 3 steps. The first is query request. Consider a client U, the data user issues the following query. Select A from R where FW is larger than A. So this is a relationship. So after the encryption, the encrypted query can be represented as as select AK from ER, which is encrypted relationship where EF is larger than A encrypted by PKU. So in this way, all the sensitive data is encrypted, but the relationships are remain. And the second thing is the result retrieve. To retrieve the case attribute values of all objects matching the specific range in encrypted relationship ER, S1 initiates secure query protocol with S2. And the SQ algorithm will be illustrated later. And finally is the result return. Then receiving the encrypted data, encrypted results from the S1. The client U decrypts it using his own key SKU by the decryption algorithm to get the final result. So the algorithm 1 is the secure query protocol, and all the keys are generated in this initialization step, and all the key generation rules or techniques are using the state-of-art key generation techniques by other authors or other proposed works. So these two protocols um, have the same functionality to process the queries, and by encrypting and decrypting the data. The only thing different between these two algorithms is the second algorithm, the algorithm 2. It's utilizing a new concept of the data packing, uh, which is illustrated in the formula in the left. And by the utilization of data packing, the efficiency is greatly improved. So in the final edition of the system, the data packing based SQ secure query protocol is used for the model, and indeed illustrating a very good performance among all the state-of-art data encrypting cloud service systems. And for this part is the experiments. The authors implement the proposed model MKSDB in approximately 3,000 lines of the C++ code on the top of MySQL. And the system only calls SQL on the C++ interface without modifying the kernel. The experiments are conducted on two Amazon machines. So both S1 and S2 are utilizing the Amazon services, which is not optimal according to the statements made by the authors before, because if both of the clouds, the S1 and S2, are provided service by the same provider, there exists the risk and possibility that the service provider can access the clouds and extract the information that are not preferred to be known. So in these graphs and figures, where in figure 3, with the fixed bit length of value, we can see the number of objects. The XXL is the number of objects n. With the n growing, the time cost is also growing, and the SQ, which is the black the black curve, um, is the time cost is growing very fast and in a not desirable lope. But the red one is an improved one, so is the SQ with extra data packing technology. It, it surprisingly illustrating the best the best performance among the four comparable systems. Notably, the blue one, the PSRQ, is an advanced secure range query scheme based on Paylayer crypto system. And that system also adopts the two-cloud structure but does not support multiple keys. So they're similar but not the same. And the GCSRQ is the garbled circuit by using the state-of-the-art framework of EMP toolkit. So the PSRQ and GCSRQ are the other popular secure guarantee query system. And as we can see in figure 3, the DPSQ outperformed all the rivals, and in figure 4, the PSRQ is slightly better than the DPSQ, which is proposed by the paper, but still the difference is trivial. So finally, here comes the conclusion. In this paper, the authors propose MKSDB, a multi-key secure database, a secure cloud database for efficient range queries under multiple keys. The system is designed to allow multiple clients to construct a federated encrypted database for the clouds to securely execute range queries on the multi-key encryption data. The authors proposed a secure query protocol and a performance improved protocol with application of data packing, and it is data packing based secure query protocol, DPSQ, which is the final form of the final system. And the system is tested in experiments and shows the performance of efficiency and effectiveness. So there are still some drawbacks of in this paper of the model, because first is the most explicit that the experiments in the experiments all the clouds are provided by the same provider, which are not that realistic according to the authors. And the second is the paper does not propose any novel key generation schemes, which is all the keys are generated by the state-of-art schemes, which are somehow predictable in some way, and also the theoretical analysis are um, are notably um, not proving uh, the security guarantee very strictly. And also, the computational complexity of the scheme is discussed, but is not proved and showed in the paper. The advantages are very obvious that the system adopts a more advanced and sophisticated structure and providing the security features for multiple clients, multiple data contributors, and data users without requiring each other's private keys, which are good. Um, and also, the system has the properties, uh, the properties that the related work had only a part of them, but not all of them. So in all, this work is very heuristic and worthy to study, and uh, based which the research can be uh, uh, can be improving. Um, Based on this work, maybe we can continue to improve some of the query performance over a larger database and extend the system to support more varied queries um, in more different types of the structure of the data. So thank you very much all for listening, and this is all for the presentation. Thank you.